So welcome you back to this module. In last module, we studied asymptotic properties of method of moment estimators. Now you had seen in the last course that method of moment estimators is a very convenient method of estimating parameters. So in the last module, we saw that method of moment estimators, whenever they exist under certain regularity conditions, they are consistent. So they have a desirable property that they are consistent. Not only that they are consistent, they are also asymptotically normal with convergence rate as 1 upon root n. So in today's module, what I'll do is I'll consider a few examples to illustrate how to find method of moment estimators and then exhibit their asymptotic properties, which in our last module we proved in certain sense theoretically, those properties. So let us look at this example. The first example I look at gamma. Now if you recall your last course, whenever you talked about gamma, you took shape parameter to be known and scale parameter to be known. So if you talk about maximum likelihood estimator, it becomes very easy. But if the shape parameter alpha is also known, then method of maximum likelihood estimation takes you to solving two simultaneous equations for which the closed form solution does not exist, and possibly you have to go for numerical solutions. So let us see x1, x2, xn, IID with common PDF. F theta x, which is 1 upon gamma alpha, mu to power alpha e to power minus x by mu, x to power alpha minus 1 for x positive, and density is 0 otherwise. So here both the parameters mu and alpha are unknown, which basically belongs to 0 infinity square. So mu can be anything from 0 to infinity, alpha can also be from 0 to infinity. So let us look at what happens to method of moment estimator. So there are two parameters, so I try to find out the first two population moments. So m1 theta, which is expected value of x1, is nothing but mu alpha that you know. What is m2 theta? Expect loop x1 square, and in the gamma case, expect loop x1 square you know is nothing but alpha into alpha plus 1 mu square. So what does the method of moment estimator says? Equate first population moment mu hat alpha hat as 1 upon n summation xi, which is basically x bar, and then alpha hat into alpha hat plus 1 into mu hat square is nothing but 1 upon n xi square. So what I do is I try to solve these equations. One can see that inverse transformation is 1, 1, Jacobian would be non-zero. So what do you get from here? Mu hat square, alpha hat square, which is x bar square, that goes over here, and then alpha hat, mu hat, and I can replace by mu hat, which is same as x bar. So you get x bar square plus x bar mu hat is nothing but 1 upon n summation r is equal to 1 to n xi square. So mu hat turns out to be s square by x bar, where s square is nothing but 1 upon n xi minus x bar whole square. Now if that is the case, then alpha hat turns out to be x bar by mu hat, which is x bar square by s square. Now you can see here M1 theta and M2 theta are continuous. Theta. In fact, they are very nice functions. Mu alpha, alpha into alpha plus 1 mu square, differentiable, and all such properties, all nice properties which you can think of are possessed by M1 theta and M2 theta. In fact, you can look at Jacobian of course, this has to be 0. Why? Because we have seen that the solution is unique. So del M1 by del alpha, which is mu, del M1 by del mu, which is alpha, del M2 by del alpha, which is twice alpha plus 1 mu square, alpha by del mu, which is twice alpha into alpha plus 1 mu. So you can see that this turns out to be alpha mu square, which is always positive. So solution is unique. Now, by weak law of large numbers, you know that x bar goes in probability to mu, sorry, alpha mu, by weak law of large numbers. By weak law of large numbers, 1 upon n summation xi square goes to x proof x square, which is alpha into alpha plus 1 mu square, and x bar goes to alpha mu square. So difference would go to alpha mu square. So what you see is s square goes in probability to, yeah, 1 upon n summation xi square, that goes to x proof x1 square. X proof x1 square is alpha into alpha plus 1 mu square minus expected value of x1 x bar square. X bar square goes to alpha square mu square, which is nothing but alpha mu square. Right. Now, if that happens, then you know that mu hat, which is a square by x bar, goes in probability to, because by Slutsky's lemma, convergence in probability is preserved by continuous transformations. All these transformations are continuous. So this goes to alpha mu square upon alpha mu, which is same as mu. What about alpha hat, which is x bar square upon s square? X bar goes in probability to alpha mu, so x bar square goes in probability to alpha square mu square. S square goes to alpha mu square, same as alpha. So there is consistency. Of course, one can here talk about the asymptotic distributions also. Root n alpha hat mu hat minus alpha mu goes in distribution to normal to 0 sigma. So let me just give you a hint how to go about it. So for that, first I apply the central limit theorem on root n and the first two sample moments. So mean vector. So 1 upon n summation I is equal to 1 to n xi, and 1 upon n summation I is equal to 1 to n xi square. Of course, when I center it, the first component of center will be expected value of x1. Expected value of x1 we have seen is nothing but alpha times mu. Then second would be centered around expected value of x1 square. Expected value of x1 square we have seen is alpha into alpha plus 1 mu square. All right. Goes in distribution to n2, mean vector as 0. What will be the variance covariance matrix? The first diagonal element would be variance of x1. What is the variance of x1? variance of x1 alpha mu square. Then this would be covariance between x1 and x1 square. This would also be between covariance of x1 and x1 square. And what would be this? Variance of x1 square. In fact, covariance of x1 square, you know, is nothing but expected value of x1 cube minus expected value of x1 into expected value of x1 square. Expected value of x1 cube, you know, is nothing but gamma alpha plus 3 upon gamma alpha. So alpha plus 1 into alpha plus 2 mu cube. This is nothing but alpha mu. This is nothing but alpha into alpha plus 1 mu square. You can simplify this. In fact, you can see that alpha into alpha plus 1 is coming common. Mu cube is there, so alpha into alpha plus 1 goes common. Alpha plus 2 minus alpha, alpha get cancelled, is a 2 alpha mu cube. What is the variance of x1 square? Expected value of x1 to power 4 minus expected value of x1 square whole square. What is expected value of x1 to power 4? Gamma alpha plus 4 upon gamma, so that means alpha plus 1, alpha plus 2, alpha plus 3 mu to power 4 minus expected value of x1 square whole square, which is same as alpha square alpha plus 1 whole square mu to power 4. So what does that become? Alpha into alpha plus 1 you can take common. Then of course mu to power 4 would become, then becomes alpha square plus 5 alpha plus 6 minus, here only alpha into alpha plus 1, so alpha square minus alpha into mu to power 4, which is alpha into alpha plus 1, alpha square gets cancelled. So 4 alpha plus 6, so 2 you can take outside, so 2 alpha plus 3 mu to power 4. So this parameter. Now what you want to do is, here you want to get mu and here you want to get alpha. So you have to consider a transformation so that here I get mu and here I get this thing, and the inverse transformation you know, and you can get the distribution of alpha hat and mu hat. So let me not just do that. You can do it of your own. Let us do another example. So you can use the delta method now. MME may not be a function of minimal sufficient statistic. Sufficient statistic. So let's look at x1, x2, xn are IID uniform 0 theta. Theta belongs to capital theta, which is 0 to infinity. So there is only one unknown parameter, so I just need to consider only first movement. So what is m1 theta? Which is expected value of x1. Mean of uniform 0 theta is theta by 2. So what I need to do is, I need to put theta hat by 2 is 1 upon n summation I is equal to 1 to n xi. So what do you get? 2x bar is the MME. So theta hat, which is 2x bar, is the MME. And what is the minimum sufficient statistic in this case? xn. Largest order statistic. So x bar certainly is not a function of xn, because if you know xn, you cannot get x bar. Because if x bar was a function of xn, I would be in a position to get the value of x bar from the value of xn. That is not happening. No, so what it means is if one has to look at the Rao-Blackweiss one has to do, one can improve upon theta hat under this loss function. So what is the estimator? So theta double hat, which is expected value of theta hat given xn, improves or dominates method of moment estimator theta hat by Rao-Blackwell theorem, because Rao-Blackwell theorem says if your loss function is convex, any estimator which is not depending on a minimal sufficient statistics or a complete sufficient statistic can be improved upon by this conditioning. Note that when I condition this, because xn is sufficient, conditional distribution of x given xn is not going to depend on theta. So when I take this expected value will not depend on theta. So it will be a proper estimator. So this is same as 2 times expected value of x bar given xn. So I have to find what is expected value of x bar given xn. So what I do is I write down this as 2 times expected value of xn into x bar by xn. I want to use the Vasu's theorem. Now given xn, this xn is a constant, so this can go outside. Now note that xi's are uniform 0 theta. That means if I define yi's to be xi by theta, then yi's are uniform 0 1. So if I define yi to be xi by theta, then y1, y2, yn are IID uniform 0 1. So that means distribution of y's does not depend on any theta. What I do over here is I write down x bar in terms of yi's. Yi is nothing but xi by theta. So xi is yi times theta. So x bar would be theta times y bar. Xn is a maximum of x1, x2, xn, which is a maximum of theta y1, theta y2, theta yn, which is same as theta is common to all of them. So theta times maximum of y1, y2, yn. So theta comes outside. So theta comes outside in the numerator and denominator. So it becomes y bar upon maximum of y1, y2, yn. But distribution of y does not depend on theta. So this suggests that x bar upon xn is ancillary. And in the uniform 0 theta case, you have already shown in your last course that x sign is complete sufficient. So complete sufficient is independent of ancillary by Vasu's theorem. So this is same as 2 times xn times expected value of x bar given xn. Now finding expected value of x bar given xn is not difficult. Again, I can use the Vasu's theorem. Note that expected value of x bar can always be written as expected value of x bar by xn into xn. By Vasu's theorem, these two are independent. Just now we have seen. Xn is a complete sufficient, this is ancillary. So this would be same as expected value of x bar by xn into expected value of xn. Now expected value of x bar would be same as expected value of x1, and expected value of x1 is nothing but theta by 2 is same as expected value of x bar by xn. And expected value of xn you already found out in your last course. It is n upon n plus 1 theta. So theta double hat turns out to be 2 times xn, and expected value of x bar given xn. X bar given xn is nothing but n plus 1 upon, which is nothing but n plus 1 upon n xn. And if you recall from your assignment problems, this is the minimum risk estimator in the uniform 0 theta case. Now, finally, let me take, now you can talk about the consistency of method of moment estimators. So, for example, you know that root n x bar minus theta by 2 goes in distribution 2, normal 0. How much? Theta square by 12, right? Because variance of x1 is theta square by 2. So what do you get? By apply the delta method, so that means h of x I consider 2 times x. So 2x bar minus theta goes in distribution 2. 2 prime. So 2 times this. So when it becomes, so it becomes 2 times normal 0 theta square by 2 is same as normal 0 4 into theta square by 12. So theta square by 3. So root n twice theta hat, sorry, theta hat minus theta so MME is consistent and asymptotically normal. So this will be root n. Right? So it is consistent because rate of convergence of asymptotic distribution is root n. So theta hat would go in property to theta. So now let me finally do an example where you may need additional population and sample movements to get the MME, because some of the early movements, when you calculate, they do not depend on theta. So as I had mentioned before, one such example is normal 0 sigma square. So let's look at x1, x2, xn, IID, normal 0 sigma square. Sigma square is positive, is unknown. So what is m1 theta? m1 sigma square is expected value of x1 is equal to 0. So if I have to use so there was only one parameter, so if method of moment estimator one has to use, it says that you put 0 is equal to 1 upon n summation I is equal to 1 to n xi. But this is absurd. It says x bar is 0. You don't get any equation in terms of theta, so you cannot talk about solving such an equation. So what we had suggested in such situations, I ignore all such equations where one of the population movements does not depend on parameters. I go to the next higher movements. So I look at what is m2 sigma square, which is expected value of x1 square, which is same as sigma square. So it says ignore this, take this, and replace sigma hat square as 1 upon n summation I is equal to 1 to n xi square. Of course, even this estimator has very nice property, consistency, asymptotic normality, because it is a mean of xi squares, and mean of any quantities of IID observations has nice property. So sigma hat square goes in property to expected value of x1 square, which is sigma square. So these are modified MME. Because the first movement does not depend on any parameter. So even modified MME is consistent. Not only that, since it is a sample mean of xi squares, by central limit theorem, you know that root n sigma hat square minus sigma square will go in distribution to normal 0, and then variance of x1 square. What is the variance of x1 square? which is expected value of x1 to power 4 minus expected value of x1 square whole square. What is the expected value of x1 to power 4? How do you calculate? Of course, this you can get from normal, because normal 0 sigma square has a kurtosis 3 sigma to power 4. So this is nothing but kurtosis of normal 0 1. That is the one way. Other way is, you know, is x1 is normal 0 sigma square. So x1 square would be nothing but sigma square chi square on 1. So what would be the variance of x1 square? It will be sigma 4 times variance of chi square, so which is 2. So 2 times sigma 1 to power 4. So these are a few of the examples which illustrate that method of movements have a lot of desirable properties, especially they are consistent, they are also can. Now what we'll do in the next module is, of course I leave that exercise in the gamma case, find the inverse transformations and show that joint distribution of method of movement estimators is asymptotically normal. I had almost done. I had shown that 1 upon n summation xi, 1 upon n summation xi square minus corresponding parameters have a asymptotic normal. Now you have to apply the delta method through inversion and show that alpha hat and mu hat have asymptotic normal distribution. So you can do it of your own. It will be a good exercise to do. So in the next module, what we'll do is we'll discuss the asymptotic properties of maximum likelihood estimators, and we'll see that maximum likelihood estimators have a lot of desirable properties. So that's all for this module. Thank you very much.